when you are ready, you can start.
A very good morning to all the panelists today. We are from Cyan Chemical Consultancy, and our plant design member is intern which is Sabrina Yogan, and our plant manager is Dr. Zaki. Our plant is aimed to produce 50,000 metric ton of sodium chlorate. Next.
So first, I would like to present about the improvement of our project based on the previous interim evaluation. First, we have changed the flush column to settling tank in order to remove the impurities. And we have also changed the phase of stream 29 from mixture to solid. Next, we have also added some details in the PFD. This is the before, and this is the after. Only the stream condition is added. The mass and energy balance are not added to avoid redundant as it is already available in the stream table. Also, the crystallizer used in the plant design is in continuous mode, so no need multiple equipment running at one time. We also include the reference for the metrics for process selection, which is from American Society of Quality. It is already included in the report. Lastly, for our improvement, we already reduced the decimal point in the summary table from 5 to 4.
Okay, let's move to heat integration. Next. The main objective of performing heat integration is to identify a visible heat exchanger network in order to minimize the usage of heating and cooling utilities. Let me explain how we perform the heat integration. Okay, first the thermal data, all relevant thermal data for such as T source, T target, and the stream enthalpy are extracted from the previous chapter, chapter 2, and the FCP is calculated based on the delta H and delta T, and the delta T mean is calculated is used in this calculation is 10 degrees Celsius. Next. Okay, the shifted temperature and the enthalpy data from the previous table are inserted in the problem table as shown in the slide. Next. This is followed by the heat cascade diagram. A heat cascade diagram is drawn accordingly in order to identify the pinch temperature, QH mean and QC mean for the entire plant. Next. The grid diagram for the full heat exchanger network is shown in the slide, and the hot stream and the cold stream is paired by following the rule FCP out is greater than equal to FCP in for below and above pinch. Next. This the maximum energy saving for the process heating and cooling requirements are as follow. For heating is 48% and for cooling is 77%. Next. This is the heat integrated process flow diagram, and as we can see, there are 4 heaters and 2 heat exchanger and 1 cooler after the heat integration. Next.
So next is the equipment sizing and costing. Next.
Optimization dulu.
Not in the process. Next. The process optimization is carried out on the crystallizer. The optimization is to minimize the utility duty of the crystallizer, and to determine that we use the temperature, utility duty, and also the magma density. The constraint for the crystallizer is the pressure is remain at the 1 atm and the temperature range is between 10 to 30 degrees Celsius. Next. And showing that optimal value. The graph, we can note that the optimal temperature is 17 degrees Celsius. Next. Through the optimization from 20 to 17 degrees Celsius, we have the utility saving up to 8%. Next.
So next is the equipment sizing and costing. Next. The first equipment is the salt dissolver. We have 2 salt dissolvers in our plant. The first one is 4.9 meter cube with 41,000 ringgit for the costing, and another one is 26 meter cube with 110,000 ringgit for the costing. Next. Next is the brine purificator. The average volume of the brine purificator is 4.94 meter cube and the average cost is around 41,000 ringgit. Next. The sizing and costing for the settling tank. The average of settling tank volume is 9.88 meter cube and the average cost is 54,000 ringgit. Next. We have 2 storage tanks in our plant. The first one has the capacity of 11,000 gallon with 116,000 ringgit for the costing, and another one has the capacity of 335 gallon with 27,000 ringgit for the costing. Next. This is the flash column with 18 meter height and the volume is 317 meter cube. The cost of the flash column is 271 ringgit. Next.
For the electrolyzer, the type used is monopolar type, 60 electrodes in total with 5 to 8 millimeter distance in between. The cell voltage is around 4.2 to 4.8 volt. The bare module cost for this electrolyzer is around 430,000 ringgit.
The equipment sizing for the crystallizer. The inner design for the crystallizer we use is jacketed scrap wall, and the crystallizer volume is 70 cubic meter. The total cost will be around 592,000. Next.
Okay, this is the specification and costing for heat exchanger 1 and 2. For heat exchanger 1, we are using 3 6 shell and tube, and while for heat exchanger 2, we are using 1 2 shell and tube. The number of tubes for the heat exchanger 1 is 1,946, while for heat exchanger 2 is 450. And the bare module cost for the heat exchanger 1 is around ringgit Malaysia 1 million, and for heat exchanger 2 is 480,000. Next. As I mentioned before this, there are 4 heaters after the heat integration. For the first 3 heaters, we are using LPS as the heating medium, and the H003 for H003, we are using MPS as a heating medium. Since the heat transfer area is less than the 200 feet square, double pipe heat exchanger are used for the heater for all the heaters. And the mere module cost for the heaters are shown in the slide. Next. Okay, next is the cooler. Chilling water is used as a cooling medium, and for the heat cooler, we are using 1 2 shell and tube, and the number of tubes used in the cooler is 440, and the bare model cost is around ringgit Malaysia 371,000. Next. For dryer, we are using ZLG series of vibrating fluidized bed dryer in order to reduce the moisture content of the sodium chlorate product by using air. And this is the continuous drying, and the bare model cost for the dryer is around ringgit Malaysia 64,000. Next. So the final equipment sizing is the centrifuge. For centrifuge, we are using 2-stage pusher centrifuge with the HR series. And for your information, HR series is a kind of 2-stage horizontal pusher filtering centrifuge which can operate continuously. And the bare model cost for the centrifuge is around ringgit Malaysia 101,000. Next.
So next is the mechanical design. Next. We choose the flash column as the equipment for our mechanical design. So the material of the flash column is carbon steel and it is a vertical column. Next. Here is the front view of the flash column. Based on the calculation, the inner diameter of the column is 4.7 meter with 12 mm thickness, and the height of the column is 18.6 meter. We have 2 manholes at the side of the column, which is one at the top and one at the bottom. Next. So this is the details of the flash column. The support used for the tank is the skirt support. The support height is 1.5 meter with 20 millimeter thickness, and the manhole size is 24 inch. Next.
Moving on to waste treatment of the sodium chlorate plant. The objective of waste treatment is to remove any unwanted species that is produced during the production. As you know that it is impossible to completely convert the raw material and completely purify the product. Hence, there will be some waste generated from this plant. From the table, it shows that there are 2 types of waste produced, which is solid sludge and gas. This is the waste treatment for solid sludge phase. Solid sludge waste is generated during the brine purification process. The impurities of the brine, which are calcium sulfate, magnesium hydroxide, and calcium carbonate, are being separated from the main brine through settling tank. The alternative for the sludge waste treatment is either filter press process or decantation process before being sent to the landfill. This is to reduce the volume of the solid waste by separating the liquid and the solid. Filter press process is chosen to treat the solid sludge waste. This is because this process is more suitable for a slurry sludge waste. easy to maintain, able to capture a high amount of solid, and consume less energy than decantation. First of all, the impurities from the brine purificator are pumped into a holding tank, and from that the slurry is pushed into flat filter press and subjected to high pressure for dewatering. The solid cake is collected in a tank and sent as gather waste to the nearest landfill, which is Kualiti Alam in Negeri Sembilan. The other type of waste generated is gas. Hydrogen is produced from the electrolysis process and hence is discharged from flash column 1. The untreated hydrogen gas can give bad impact to the environment. Hence, it is best to use the hydrogen gas as fuel to generate electricity through fuel cell. The hydrogen gas produced from the process contains some chlorine gas, making the purity of the hydrogen decreases and will also decrease the efficiency of fuel cell. Therefore, the alternative used to treat the gas is either using gas scrubber or cryogenic distillation. Gas scrubber is chosen to treat the hydrogen gas as it is cheaper. The scrubbing liquid is easily obtained and affordable, high removal yield, and simple technology. From the figure, fan is used to transport the gas easily into the gas scrubber. Scrubbing liquid, which is water, is sprayed from the top of the vessel and capture the chlorine as the hydrogen gas passes through, and then the chlorine and scrubbing liquid will accumulate at the bottom of the vessel, while the treated hydrogen gas will exit through the top outlet. Since the scrubbing liquid will be acidic, sodium hydroxide is used to neutralize it and recycle back to the droplet separator.
Process control. Next, the process control is focused on the temperature, level, and also the flow. The temperature, we intend to maintain the temperature of the crystallizer at 17 degrees Celsius. So we have one control loop for the temperature, and there's a control valve to control the flow rate of the cooling medium in order to control the temperature. And then we have the level of the level of the crystallizer. We will control the flow rate of the outlet stream in order to achieve the desired level of the crystallizer. And then we have the flow indicator for inlet stream and also the outlet stream. And they are also installed together with the alarm. So when the flow of the outlet stream and the inlet stream is below or above the set point, the alarm will be activated and the operator will be notified that whether there's a pipe linkage or the pipe blockage. Next.
For the process control of electrolyzer, there are a total of 4 loops. The first loop, which is loop 116, is used to bring the materials into the electrolyzer by detecting the level in the electrolyzer and control the valve in the inlet stream. The next loop, 117, is to maintain the temperature of the electrolyzer at 65 degrees Celsius, as it is the operating condition for the process by controlling the steam flow rate. Next is loop 118, used to maintain the pH value of the inlet stream at around 6 to 7 by controlling the flow rate of the HCl mixed with the reactant. Lastly, for loop 135, it is to indicate the composition in the electrolyzer. So when the composition already reached the desired value, the outlet valve will open and the product will flow out.
Here is the process safety strategies and studies for our plant. Next. There are 5 elements for the process safety and studies, which is plant safety, emergency response, plant layout, worker safety, and hazard. Next. There are several factors that affect health and safety in our plant. The factors are people actions, the equipment, and the material, either the raw materials or the product itself. Hence, to avoid this factor, there are some examples of strategies that we can implement. For example, installing the custom safety equipment, train the employees on the proper safety procedure, and create the proper standard operating procedure for the plant or for the equipment. Next. Second is the emergency response plan. This is required to increase the safety of the plant and to keep the workers under safe conditions. There are 4 elements to complete the emergency response plans, which is prevention, preparation, response, and recovery. Next.
Next is the plant layout. Basically, plant layout describes the arrangement of facilities, machineries, and furniture within the site within the building. And the main objective of the plant layer is to maximize the efficiency of plant operation and to create a safest environment. And the last one is to keep the most economical flow of materials and personnel within the site. Next. Okay, as we all know, the safety of workers and the staff is the most important concern among all other things in a chemical plant. The worker safety describes the provision of the safe environment, equipment, procedures in the workplace. Here are some ways to achieve a good safe workplace. Provide safety training and instruction, and provide suitable PPE, and set up sufficient safety supervision. Next.
So we will move on to heads-up analysis of electrolyzer. The first parameter is pressure. When the pressure is high, caused by a chemical leak, it has possibility of the pressure in the device or piping to increase. The action required is to monitor the pressure in the system and install safety valve. Next is flow. When there is no flow because of blockage, it could lead to loss of feed to the next section of the process. Therefore, the action is to regularly inspect the process. When the flow is high due to failure of level valve, it could lead to overflow of the stream. It is best to install high-level alarm. When the flow is low due to leaking, it could lead to material loss to the surrounding. Hence, it is also important to do regular inspection. Lastly, the parameter is temperature. When the temperature of the electrolyzer is low due to insufficient heat from the heater, it could lead to incomplete reaction. Hence, the action required is to install temperature controller.
Now I'm going to introduce you with the heads-up of the crystallizer. Next. So the first parameter of the heads-up of crystallizer is the feed flow. When there is no feed flow entering the crystallizer, which may be caused by the inlet pipe linkage, and the possible consequence is that no sodium chlorate crystal are produced. So the action required is to install the flow indicator. Same goes to the less feed flow entering the crystallizer due to the inlet pipe blockage. We may have the less sodium chlorate crystal are produced. Same, we should install the flow indicator. Next. There are also possible backflow of the feed from the crystallizer, and this caused by the outlet pipe blockage or the volume of the crystallizer decreases due to the accumulation of the crystal inside the crystallizer. And the possible consequence that the agitator of the crystallizer may be damaged. So we should have a regular checking and maintenance. The next parameter is the temperature. The temperature of the crystallizer is more than the set point. So this caused by the heat is not efficiently removed. So the possible consequence that the efficiency of the crystallization process will be decreased. So we should increase the flow rate of the cooling medium when this happens. Next.
Next is the profitability. In order to have a clear vision of the economic aspect of the plant, profitability analysis is performed. Next. Okay, as we all know, the total capital investment is the one-time expenses for the manufacturing, for the construction, design, and the startup of the plant. For our plant, the total capital investment is around ringgit measures 60 million. Next. And for the manufacturing cost can be divided into two, which is direct manufacturing cost and indirect manufacturing cost. The total manufacturing cost for our plant is around ringgit measure 70 million. Next. And the next is the total general expenses, that is consists of administration cost, distribution and selling expenses, and R&D. Next. And the total production cost is the sum of the product manufacturing cost and the general expenses, and the after-tax rate of return is 87%. Next. Okay, next is the break-even. As we can see in the slide, the break-even point is about 40,000 metric ton of sodium chlorate. This means that if the production goes beyond this value, profit is guaranteed. So for our plant, we are aiming to produce 50,000 metric ton of sodium chlorate, which is more than the break-even point. Therefore, we can say that most probably we will have a shorter time to gain back our profit. Next.
Next is the cash flow, and we have three assumptions. The sale increase is only 80%, And the plant life is including the 3 years of construction. And then we have the depreciation value of 10% for the FCI. Next. From the undiscounted cash flow, we can note that the payback period is 1 year and 7 months. Next. And this is the graph of the discounted cash flow by using 10%, 20%, 30%, and also 50% for the discount rate. Next. So based on different discount rate, we have the corresponding payback period after startup in year 3. 10% will be 11 months, 20 will be 1 year and 4 months, 30% will be 2 years. And the 49.55% is the maximum allowable discount rate, which also known as the internal rate of return. It's 30 years. Next. And here is our conclusion. For our TCI is about 50 million and the total expenses is 60 million. And for the total production cost is 70 million. After tax rate of return is 86%. And the break-even point is 40,000 metric tons, correct? And our plant life is 30 years with the beginning of 3 years as the startup period. And the maximum discounted cash flow rate, IRR, will be 50%. Thank you very much. That's all from us.